So okay, coming back, I'm writing down this Fourier transform, right? This is a Fourier transform. So on this m by m patch, so with the pixel indicate m1, I mean the m1 n2 pixel is a xm1 n2. The Fourier transform is given by this, so it's a minus I 2 pi k1. I should divide by n also, divide by this is basically divided by, yeah, I can put a 1n here. And this is a sum over m1 and m2. So first thing I want to say is like, this thing is separable. So if you remember, like we have filter earlier, that I can rewrite this like m1, this is hard to run, maybe I put it down here. Sum over x m1 and 2 exponential I 2 pi and 2 k2 n, this sum over n2, but then I multiply by I 2 pi m1 k1 over n again. So first thing I want you guys to observe is that like, you can think of this as a filter, like what we did before. Right? It's like a filter, and this filter is actually separable. You can think of I'm going to do per each. Let's see, I can do each. This is let's say this is row. This is m1. Then I can do one column at a time. For each m1, I just go for a compute the Fourier transform, 1D Fourier transform along each of these columns. Then afterward, I have the Fourier transform along each columns. Then I can do Fourier transform along each row. This one is basically like the outcome after the Fourier transform across each column. Then I do this outcome, like apply Fourier transform across each row again. So then, what's the inverse transform, by the way? Maybe okay. Since I can decompose into 1D transform, right? Maybe just simplify that. Just consider 1D transform. Let's say if I have 1D, let's say a 1D signal xm1 here, and I do a Fourier transform. It's basically I 2 pi. And since 1D, maybe I don't need m1. I just use n here. Exponential minus I 2 pi n k over n. So k is basically frequency here. And this gives me that xk, let's say. This is a Fourier transform in 1D. So what's the inverse transform? Anyone kind of like remember that, like from DSP or like digital image processing? So what I mean is that how can I get xm back from xk? Oops, why? xk?
Don't you sum over the k's?
Yes, sum over the k, and kind of similar to this. Right? Yeah, we have like, but I have I 2 pi k n over n. So, and actually I will have a 1 over n factor here somehow. Actually, I like to think of like this 1 over n factor. Typically, people will do like forward, like have no this factor, no factors here, and then like when do inverse transform, they put a 1 over n factor here. But I can also make it symmetric. So if I make it symmetric, I can put 1 over square root n here, put 1 over square root n here. So, and then I like this a lot because if you think of that, what you're doing Fourier transform is really doing a projection. So I will explain what I mean. So I can define some inner product. So as two 1D factor. Let's say I have two 1D factors here, u and v. So I can define the inner product as something like un vn n. So my bar here is just the compass conjugate. So I say I have the compass conjugate there. So then this inner product, like you may have taken class in vector space or whatever, but it doesn't matter actually. Just think of I define something this called inner product. Then it has some obvious property here. So basically you see this, it has property that, for example, u1 plus u2 v is equal to u1 v plus u2 v, right? Because it's linear, and also like I have say u1 uav is equal to auv, something like that. And more importantly, it has a property of positive kind of when you are doing u non-negative inner product with itself. So this one will be just bigger than or equal to 0, right? Because like this one will be equal to n un un, so it's equal to un square, right? So therefore this will always be bigger than or equal to 0. So now what I can reinterpret is that like I can think of all of this is some kind of basis, and this is I can call it vk. I can call it vk, and note that like we have very nice property here that like if I have vk and maybe vk1 and vk2. And if I have k1 is not equal to k2, what do I have? Yes, that will give me 0, right? So basically, if I have k1 not equal to k2, I have exponential I 2 pi k1 minus k2 n over n, sum over n. But this is like a sinusoidal thing, so all just cancel out, will just give me 0 here. So on the other hand, if I have vk, I mean the same k, like vk multiplied by vk, then it will be what? Yeah, that would be just equal to 1, right? So because that would be just equal to, yeah, sum over, maybe I slow down. I don't know, because I know this one is really good, but I don't know whether the other guys is like following me. So this will be I 2 pi. I should have a compass conjugate for this guy. So I have I 2 pi k n multiplied by e I 2 pi k n. So they got cancel 1 plus 1 over n there. So therefore it's 1. So then what I mean is like if you think of what is Fourier transform, it's basically just we are trying to project whatever this signal into this sinusoidal functions, right? Sinusoidal basis. So, for example, like if I have xn, assume I can write it as c represent cv1, c1v1 plus c2v2. And so on up to Cn, Pn. So this V here is the sinusoidal signal here. Basically, Vk is equal to exponential. I use I here. I 2 pi Kn over square root n. So then what was Ck? For example, like, then what? Yes. So I take this as basis, right? I assume that my x sign can be represented as this. Actually, essentially, I should write v, and so on. This sinusoidal or whatever this things, I add them together, sinusoidal basis, and weight the sum together to form my x. So yes, but actually even before that, let's see. Even before that, like I have this equation here, right? I assume that xn can be represented as this combination. Now, how do I find ck? Let me try to do vk and a projection, or like I don't need this n, maybe just vk and x. I do a projection, right? Then projection, that what we already showed earlier, right? This is super nice, right? If you have vi or like vk1 and vk2, so this will be all 0 unless k1 equal to k2, right? So if I do this, basically I only have one term left, right? Because vk and v1 is equal to 0, vk, v2 is equal to 0. Only one term left is like ck and vk, right? Basically it's like ck, vk, vk, right? But we already know that vk is just equal to 1, right? So therefore, like ck is just equal to the projection there. And then from the definition of that projection is actually just equal to I'm sorry, like where's okay, it's just this definition here, right? So and my vk is actually I should project the other way is better, because I've seen things. I think like x, yeah, I should do it this. I should be careful. xvk, I should do this, because actually here, like I'm a bit quick about this property here, but as you can see, if I have a v u, the inner product, I should have like a bar like v u instead. Oh, yeah.
You're off page.
V u, huh? What's that?
We can't see what you write.
No, it's
Oh, here.
Where?
Yeah, here. Oh, yes. Let me write this again. So I mean, like this one here, if you think of like a u and v, because this is the original definition, right? So a u and v, that's I need to put a complex conjugate for that guy. If I pull this out, actually I have a bar u v there. So so therefore, if I want to pull a ck instead of ck bar here, so I want to do like x and vk complex conjugate there. I mean in the product of x and vk there. So then x and vk then go back to that definition is equal to actually I think I I'm not consistent with my definition, but anyway, so that this should give me back the xn, that's the I2 pi, I think I should use this one. No, I don't know where I made a mistake here, but but I should have like ck just equal to that, and that just is just it looks like I'm missing a complex conjugate somewhere, but let me summarize again. So your Fourier transform is nothing but a projection to some basis, and that basis is some sinusoidal basis given by this. Yeah, I have a tendency of not organizing. Where's my V? My original V.
Oh, you've got an arrow towards it. You've got it underlined. Yeah.
Yes, I have this here. So it's basically just projection to all this guy. And we got this because we have the property that we know that that basis is all normalized and also like they're all orthogonal to each other. So I'm actually, because it's the basis, then immediately you have some nice property that you know all along. So for example, if I look at like x and x, just I have that signal in the original basis, and then I say I can kind of like think it as like a weighted sum of all these bases, right? So I can write it as this C1 V1 plus C2 V2 and so on, and C1 V1 and C up to like Cn Vn, right? And then like, so this will give me, again, like because only Vi and Vj, and when they are the same each other, they will be non-zero. So basically, it will just equal to C1 square plus C2 square, and so on, right? Up to Cn square. So therefore, what's the name of this thing? Do you remember? I ask you because I don't remember, actually. There's a name for that, that the energy before the transform, after the transform is the same. But as long as you think of it as a projection, then it's apparently it's true. Yeah. So okay. So I think some of you guys already know this, but I think it's very nice to have as a review, because really you should think of like Fourier transform as nothing, but it's just projection to this orthogonal basis. And of course, for images, then it will be like it's like 2D orthogonal, kind of like you have both direction, right? So and we'll have this sinusoidal patches. And let's see. I guess I will just see what else in this slide here. I will just wrap this up. So and as I mentioned, like the energy is conserved in the frequency domain. Like you have the original patch of image in the spatial domain. After transform, the energy should be the same. And we have the convolution theorem also. Like that one is quite easy to show. This time I'm write it down. So basically, if you have convolution in the spatial domain, it will be just equal to Porter in the Fourier domain. And actually, it's vice versa also if you have free domain, because actually it's vice versa. If you have free domain, actually if you do a convolution in the spatial domain, it will be like plotted as well. So, and we can use this property to implement filter, right? At least in theory. So, for example, I have a filter like this. I can theoretically compute Fourier transform for this patch here and get a Fourier transform is equal to this, if you remember last time. And like this, I compute Fourier transform of this image. And oh, by the way, like one thing I forgot to mention also, do you see that this guy is symmetric? Like, do you know why it's symmetric? The Fourier transform appear to be always symmetric.
Is it because the image is real and even?
Yes, but it doesn't need to be even. Yeah, it's real, even. Yeah, it doesn't. I don't think it needs to be even.
I think it's like
Yeah.
the actual part and the conjugate part, they coexist in the.
Yes, because we are only. Brandon is very also wise. So because we are only plotting the magnitude here, so it doesn't care about the. So if you write it down, actually, actually maybe I write it down anyway. If you write it down because it's real, right? So the Fourier transform is what? It's exponential I or j 2 pi k n over n. I have n here. I have xn here. So because it's real, so if I change this frequency from like k to n minus k, so then the only difference will be the sign will change, right? So for example, if I change to n minus k here, I basically will just get this way. So because because this is real, then this is just complex conjugate of each other. So if I only look at the magnitude, so this is the same. So when I look at frequency of n minus k, we should have same magnitude as for frequency equal to k. And remember, like when we're plotting this, we always use this is a convention in image processing, and like we always take this middle point as the zero frequency here. So therefore, like it's symmetric, kind of like here, in the sense that this is 0, 0. If you think of this going this way, like how should I? Right. This is like 0, 0. If I go along this way, this eventually will go back to n minus 1 and then n again, right? N and 0 is basically repeated. It's the same thing. So therefore, it's symmetric along this center point here. And so this is some example that you can essentially do some filtering. But of course, this is a little bit, I would say, ideal. So for example, this some processing here, like this is blurred in a particular way. You can see the actual artifact in the frequency domain. I'm trying to get away this artifact here. So I try to see, like, if I exactly remove this artifact, I get a really good result here. So that's another example that this is essentially a low-pass filter. Right? Centering is a low, DC there, so therefore this is a low-pass filter. And you remember that we got this ripple here. That when we have the box filter and when we have this kind of filter here, we have ripple. And of course, if I do an inverse of this guy, I mean, instead of like taking outside as 0, I take the inside as 0, then will be exact opposite of this filter, right? So I will get a high pass filter like this one. And this is also a kind of ideal example that we have this kind of like ripple artifact that we can ideally remove. Actually, it's exactly these two dots here. I don't think you can see it, but these two bright white dots here is contributing these artifacts here. So if we kind of like set this to 0, then this artifact is gone. And I showed earlier that we have a box filter, and also like that one is not a box, but it's a circle one. But we have similar to this box filter, have this kind of like ripple artifact, right? And actually, I kind of asked like why we have this artifact last time. If you think of like what you have, again, like in the frequency, okay, remember like we have the convolution theorem, right? So if we do this filtering in the spatial domain, it's the same as doing the product in the frequency domain, right? So if we look at like what we have for a box filter, what's the Fourier transform for a box filter? Do you know? Like, do you remember? Like just a, or like maybe not even a box filter, maybe like if I have something like this, like in 1D, just a step function, like, do you remember like what's the Fourier transform for this guy here?
It's like sync.
Yes, a sync. So a sync will be like something like a lot of ripple or something like that, right? Some sign x over x, that kind of stuff. So and so therefore, because of this ripple, you have some high frequency components there, right? So therefore, this actually contribute to the artifact. On the other hand, if I have a Gaussian filter, so I have a Gaussian filter. Do you know what is the Fourier transform for a Gaussian? Yeah, it will be a Gaussian as well. So therefore, like it will kind of decay very nicely. So that's why you won't see those artifacts. And yeah, that's just repeating what I said. So this is like if you have a kind of like a box side filters, you have this high frequency artifacts like this. So, and we asked previously, like, is convolution invertible? And it depends, right? And actually it depends on, now it's become very clear, right? If you think of the frequency representation, so convolution is like you do a FFT for the original image and then do a FFT for the filter, and then you multiply them and try to kind of do an inverse FFT, you get this back, right? So when I will be able to get from here back to this one? When I will be able to do an inverse convolution, in a sense, like from this convolved image like this, like getting back to this one here.
If the function is not 0, if the function doesn't have any like holes in it. Yes. If I have here, like if I have the FFT in the frequency domain of the filter, if it has 0 anywhere, then I multiply this guy, then that one will be, the information will be completely gone, right? So therefore, it really depends on whether your filter here in the frequency domain will have any zeros there. So if it doesn't have any zeros, theoretically it will be it will be invertible.
So does that mean if I like remove a particular frequency from the image, then will I be able to get it back to?
Yeah. No, yeah, you won't be able, yeah, you make it look nicer, as I show some of those examples, like to remove the artifact, but you, of course, you won't be able to get back the original. So remember, like for frequency, the frequency representation is contain exact amount of information as your spatial representation. So it's just like in the spatial representation, if you remove a patch there, it's completely gone. So if you set 0 there, like those places set to 0, then it will be gone. So again, like if you do the same thing in the frequency domain, set somewhere to be 0, again will be completely gone. You won't get it back. So in theory, you can do deconvolution as long as your filter doesn't have zeros in the frequency domain. But in practice, for example, like this one, I have a filter. It's kind of decaying, but doesn't get zero exactly. But if you have noise, the noise will have big impact, because here you can't diminish the signal so much already, in the high frequency, and then you added the noise, then basically you amplify the noise when you try to invert the signal back. So this gives examples, if after I do the convolution, if I have noise, I'm trying to get it back, I can get pretty noisy here after deconvolution. So yeah, this is basically the same thing. Yeah, deconvolution is actually kind of I'm not sure, it's still a research topic. 5 years, at least a decade ago, it's kind of, it's still, I think it's publishable. I guess now it's hard, but I guess if you really push it, still you may be able to find places to publish. Typically, the difficulty is, of course, if you know the filter already, then you can, very simple, you just do the exact opposite as what we did here. But the problem typically is that you, for example, have a camera, you take a picture, when your hand shake, it's kind of like have a blurring effect there. It's like applying a filter there, but you don't know how your hands shake, right? So therefore, it's you need to emulate back, kind of predict what you actually did when you take the picture. So then there's so-called this blind deconvolution, so you need to figure out, use some kind of estimation to figure out what is your filter, then maybe you can get this back. This is just a remark how Fu died. He tripped himself and fell down the stair and went, I don't know, wearing a blanket. I don't know. It's just a it's interesting. It's the same time as Gawa. Also, I don't know that. I didn't know that. You know Gawa? He was a very famous mathematician. I think he died very early. Also, I think he died of in a duel. It's called a duel. Yeah, something like. Oh, it was an interesting time. So I don't know. I maybe I will just give a. Oh yeah, this is a little bit old, but maybe I will still just talk about it a little bit, because even now. When you have this image compression, video compression, still we work in the transform domain, but not necessarily in, for example, Fourier transform, or even DCT. So DCT is a stripped version of this Fourier transform. So basically, you just keep the cosine component, and you take away the sine component, and you modify a little bit the parameters as well. But basically, all these image compression techniques are similar. You do a transform, whatever transform into some frequency domain, and then the frequency domain typically for all lateral images, you will have more heavy DC component, low frequency components than the high frequency components. So we will basically throw away most of the high frequency components, or we'll compress it more. So more precisely, like for example, the old JPEG format, maybe you have kind of like allow more quantization error. So after you do a transform there, you will, like for each coefficient, you will quantize that, and quantize that with like different quantization step. Basically, like for DC, you will have a quantization step is smaller, so you have a higher accuracy, and for like higher frequency component, you have a higher step and then a lower accuracy. And then afterward, like you can just compress that like sequentially like this, say, so in a zigzag way. So depend on implementation. For example, sometimes you can even chop in the middle. Right? So you can keep on decompressing. Now you don't have any connection, you just stop here. So, but you just miss the high frequency component, you can still reconstruct. And we mentioned that already, like typically you will convert first to like YUV or like YUV or like YCBCR space. And then like for the commoners, you use a different kind of resolution. So just downsample it further. So I guess that's it. I will skip this one. There's so much I like to talk about for these slides here. Actually, I only have, okay. So maybe like instead of starting anything new, I'll just do some logistic. So I will put up a homework today. I guess I will explain that more next time, but I will put it up, then it probably will be due next Saturday. And also, like I mentioned that we should do a lottery, right, for the graduate folks here. So
next Saturday or this Saturday?
Next Saturday.
Okay.
Yeah. Don't worry about that. Yeah. It should be pretty simple, like homework also, like so the level will slowly, hopefully, it's hard to decide, slowly increase the difficulty, I guess. Let's see, I have, what is that? Oh, okay, where's that? I already put in the names for you guys. Whoa, wait a sec. I don't think this is my last version. Oops. Oh, I didn't save. Okay, anyway, I do it next time then.
Sure.
So, okay. Just now I did have this technical difficulty and didn't work out. So, okay, I guess I don't want to start anything new actually. So maybe I will stop early today. So if you guys have any questions, comments, I'm sorry about it. This is a short lecture, excluding the connection problem. Yes.
What our presentations like mine is
Oh yes, I have your name.
Yeah, when do you have to present?
I just said that like I will do a lottery in class and determine the presentation time, but I didn't save my, because I need to shut down my computer just now, so I didn't save. So I will first need to decide that.
So the presentations, it has to be like a practical one or just a you have to give some
Oh, it's up to you. But like if you want to just present like this, like it's more challenging, right? So if I guess a press slide is easier. But if you want, you can even go to the board. Like it's fine. Yeah. Yeah, sure.
What do the presentations do?
Yes.
Whenever we present what days?
Oh, I haven't decided yet. I want to do a lottery just now, but I didn't say. Like apparently, I tried to shut down everything just now. I didn't say. Thank you.
Sorry.
Sorry.
So what days do you expect people to present? Not
So the earliest day would be March 12th. So that would be like at least a month. Yeah.
Yes. The attendance like it is showing annual.
Oh yeah, it's okay. Because that's only for undergrad. Somebody else in the class.